Hello friends, welcome to Sitzer.com. Now in this video we will learn about the addition reactions of alkenes. In alkenes we know there is a carbon-carbon double bond, and in a double bond there is a sigma and the pi bond, right? Pi electrons are loosely held electrons. Sigma electrons are strongly bound electrons. So pi bond can easily be broken down, whereas a sigma bond is a stronger bond. It is due to the pi electrons that the alkenes are reactive than alkanes, right? Alkenes are more reactive than alkanes because of the pi electrons. So over here in the alkenes, electrophiles, which are electron deficient species, can attack on a carbon-carbon double bond, right? An electrophile can attack on a carbon-carbon double bond because of the pi electrons, because pi electrons loosely held electrons, loosely bound electrons. So pi bond can easily break down. Because of the pi electrons, alkenes undergo addition reaction. You can break the pi bond, and by the addition of a reagent AB across a double bond, you get a saturated compound. So alkenes can undergo addition reaction. But what type of addition reaction it is? It's an electrophilic addition reaction. So the most common addition reaction is in alkenes is electrophilic addition reactions. So let's just check the mechanism. How does this reaction actually occur, right? How this addition reaction occurs. First, the reagent AB, it will dissociate into an electrophile and a nucleophile by the hydrolytic bond fission. Suppose here both electrons, they shift towards the atom B, and you get a electrophile A plus and you get a nucleophile B negative. Due to the presence of pi electrons in alkenes, electrophiles will attack on the carbon-carbon double bond, and it forms a bond with it. The pi bond breaks down and it forms a bond with the atom A, right? And you get a carbocation. The intermediate over here is carbocation. This is the first step, attack of electrophile on the alkenes. In the second step, on the same carbocation, now nucleophile here, the nucleophile here is what? The B negative, right? Nucleophile, the B negative will attack on it, and you get a carbon-carbon single bond with the atom A over the carbon over this carbon and the atom B over this carbon. So this is the overall addition, right? This is how the electrophilic addition reaction occurs in alkenes. The intermediate here is carbocation, right? This is the intermediate that we get during the electrophilic addition reactions of carbocations. During the electrophilic addition reactions of alkenes. Now let's take an example of the addition of hydrogen halides. Hydrogen halides, like suppose we have HCl, HBr, HF, right? HI, different hydrogen halides. So in general we write down them HX, hydrogen halides. Hydrogen halide can also add across a double bond with one atom carrying hydrogen and another atom carrying the halogen. So how does this reaction actually occurs? The mechanism is the same that we studied previously. First, hydrogen halide will dissociate, in the first step, hydrogen halide will dissociate into H plus and the X negative, right? In the second step, it is the attack of electrophile of the carbon-carbon double bond. So when there is attack of electrophile here is the H plus, so it will attack on this one, and what you get? You get a carbocation as an intermediate, right? In the next step here, the same carbocation that is formed here in the step number second, right? The carbocation, it will be now under the attack of nucleophile. So one carbon gets a hydrogen, another carbon gets halogen, right? So this is an addition reaction of alkenes. Different hydrogen halides have the different reactivity towards a particular alkene. Suppose we got here an alkene, we have ethene, this is C2H4 and ethene, and when hydrogen halide reacts with it, different hydrogen halides have the different reactivity. HI is the fastest, right? HI is the fastest and HF is the slowest. So with the HF it has the slowest rate of addition, with the HI it is the highest rate of addition. Reason, because in HF the bond strength is very high, the bond dissociation energy is high, and while as HI the bond length is more, bond dissociation energy is less, so it is easy to add the HI across a carbon-carbon double bond than the HF. So the reactivity increases from HF to HCl, then HBr, then HI. Why? Because the bond length from HF to HI increases and bond dissociation energy decreases from HF to HI. That's why the reactivity of hydrogen halides increases from HF to HCl, HBr and HI, with the HI having the fastest rate of addition reactions. So let's take here a couple of examples, right? So if you take an alkene here, CH2 double bond CH2, and we add here the HBr. So what happens here? Now the HBr will add across a carbon-carbon double bond. So you get the CH3 single bond CH2Br, right? Similarly, if we take alkene ethene and we react with the HCl, again what you get? You get the CH3 CH2 Cl here, right? And if we take alkene CH2 CH2 and HI, what we get? We get the CH3 CH2I, right? So these are the different alkyl halides we get by the addition of hydrogen halides to the alkenes. If we have asymmetrical alkene, right? In an asymmetrical alkene, how the addition of HBr can take place? The addition of HBr or any halogen halide follows the Markovnikov's rule, right? This is the important rule here. In our previous examples, we were discussing actually the addition of HBr, HCl, HI to a symmetrical alkene, but this is not a symmetrical alkene, right? Symmetrical alkenes have the same groups across a double bond, but this is asymmetrical alkene, right? Because we have a carbon-carbon double bond, and to the one side there are two methyl groups, to the other side there are two hydrogen atoms, so the groups are not same, right, across a double bond. So this is asymmetrical alkene. For asymmetrical alkene, how does this HBr can add, right? It follows actually the Markovnikov's rule. What the Markovnikov's rule says? According to the Markovnikov's rule, hydrogen adds to that double bonded carbon that has more number of hydrogen atoms. Okay, hydrogen adds to that double bonded carbon. You know, we have a carbon-carbon double bond here. One carbon has two methyl groups, one carbon has two hydrogen atoms. So as per the Markovnikov's rule, hydrogen adds across a double bond with more number of hydrogen atoms. So that means hydrogen will go over here, and then what do you get an intermediate? A carbocation will be here, right? Okay, so as per the Markovnikov's rule, hydrogen will add across a double bond, but hydrogen will go to the carbon that has more number of hydrogen atoms, right? So it is like this. Now when the hydrogen goes over here, you got a carbon-carbon double bond. Now the carbon-carbon double bond breaks and you get a CH2 and then one more hydrogen over here, and now you get a CH3, right? You get first a carbocation over here, isn't it? Because when hydrogen electrophile H plus, it attacks on the carbon-carbon double bond, with the hydrogen adds to the double bonded carbon that has more number of hydrogen atoms. So this particular carbon has got two hydrogen atoms, right? So, and this one has zero hydrogen atoms. So this is rich in hydrogen atoms. So the hydrogen, as per the Markovnikov's rule, it goes to that double bonded carbon that has more number of hydrogen atoms. So when the hydrogen goes over here, you get an intermediate, a carbocation, or this one, right? So this is a tertiary carbocation, right? This is a carbocation, correct? But in the second step, what happens then? The Br negative will attack on the same carbon atom here, right? Now the Br negative will attack on the same carbocation, and what do you get the product? You get the product like this. Carbon-carbon single bond, Br2 over here, and now this is the CH3. The CH2 now becomes CH3, and there are two methyl groups also, and this is the product that you get, right? This is as per the Markovnikov's rule. Now question is why? Why this hydrogen should go to the carbon that has more number of hydrogen atoms? What if this hydrogen attacks on this carbon, right? In that case, the bromine will go to the CH2. So then let's see what happens then, right? When the hydrogen adds to this particular carbon over here, right? To this particular carbon, you get an intermediate over here, right? You get a carbocation, but the carbocation will be here, right? Okay, so you get a carbocation like this, right? So we actually have a CH3, CH3, and when this particular hydrogen attacks on this carbon, you get a carbocation like this, CH2 plus. And this is a 1 degree carbocation, right? This is a 1 degree carbocation, and in that, after that, what will happen? The Br negative, the nucleophile, will attack on the carbocation, and what do you get then? You get this one, right? You get the product like this, CH2 here and the Br over here, and this one, okay? But this addition, if you compare this addition here and the addition as per the Markovnikov's rule, you see that there is a difference in the stability of the carbocation. Over here you get a 1 degree carbocation, but over here you get a tertiary carbocation. This is a 3 degree carbocation, and we know the order of stability of the carbocations is, what is the order of stability of the carbocations? Carbocations, the order of stability is tertiary is more stable than secondary than primary, right? Okay, so therefore always the reaction follows the more stable reaction intermediate, right? Take another example, right? Again we have an asymmetrical alkene. We got these two carbon atoms, right? Okay, the two carbon atoms over here, and when hydrochloric acid adds across this double bond, we got this particular carbon here, it has one hydrogen atom, and this one does not have any hydrogen atom. So as per the Markovnikov's rule, hydrogen goes to the double bonded carbon that has more number of hydrogen atoms. So that means hydrogen will attack on this particular carbon, and the chlorine will go to this particular carbon, and then you get a product like this. You get a product like this. The double bond breaks and you get a one more hydrogen over there, and you get the chlorine over here, right? Or simply I can write it like this, right? This is the Markovnikov's addition. Anti-Markovnikov addition also occurs, but that product is formed very small, in a very small quantity, right? That's not the major product. You also get the anti-Markovnikov product, but that is what? In a very, very small amount, right? So that's not a major product. So let's take another example here. If we got a double bond, okay, and when you add here the HBr, as per the Markovnikov's rule, hydrogen will go to the double bonded carbon which has more number of hydrogen atoms. You actually have here the CH2, right? So the hydrogen will go to this particular carbon, and the bromine will go to this particular carbon. So when the double bond breaks, the bromine will be over here, and the CH2 will now be the CH3, correct? This is called as the Markovnikov product, right? This is the Markovnikov product. Why? Because this is the product that we got as per the Markovnikov's rule. Let's take some other examples of the addition reactions, asymmetrical addition reactions of alkenes. Suppose we got the CH3 single bond, CH double bond and the CH2. If you add HBr, so what is the intermediate that we get? We'll follow the Markovnikov's rule. It will go to this carbon because it has two hydrogen atoms. So you get intermediate like this, CH3 single bond, CH single bond, CH3 now, and the intermediate will be over here. Okay? Then in the second step, the Br negative will attack on it, and the product will be the CH3 single bond CH Br CH3. This is the Markovnikov's product, because the addition follows the Markovnikov's rule. Hydrogen adds to that double bonded carbon that has more number of hydrogen atoms. But if the same hydrogen atom attacks on this carbon, then what will be the product? The intermediate then will be like this, CH3 CH2 now, and the intermediate is over here. The carbocation will be a 1 degree carbocation, right? If it follows the attack B, right? So the product will be then this molecule, right? Okay, this is the A addition, which is actually the as per the Markovnikov's rule. But if it attacks on the central hydrogen, the carbon, if it attacks on the central carbon, the carbon that has less number of hydrogen atoms, right? Then this will be the intermediate, the 1 degree carbocation, right? This is a 1 degree carbocation. And over here, what we got? We got a 2 degree carbocation. And among the two carbocations, 1 degree is less stable, 2 degrees more stable. That's why the major product is always this one, right? So then, if over here the Br negative attacks on it, right? Then what you get? You get the CH3 single bond CH2 CH2 Br. So you get a 1 bromopropane. You got here the 2 bromopropane, and this is the 1 bromopropane. But this is anti-Markovnikov's product, right? And it will be a minor product, right? Anti-Markovnikov's product. This will not be a major product. This is a minor product, right? Let's take one more example over here. Suppose we got this molecule here, and over here is a double bond, and you got a CH3 here, and you have a hydrogen over here. When I add HCl, now there are two possibilities: either it may follow a Markovnikov addition or anti-Markovnikov addition, right? So if suppose hydrogen goes over here, attacks on this one, so it is as per the Markovnikov's product, right? Because among the two carbon atoms, right, this carbon and this carbon, the hydrogen is over here, and this particular carbon does not have any hydrogen atom. So this is the carbon with more number of hydrogen atoms. Among the two double bonded carbons, hydrogen will go over here, and the chlorine will attack on this one. So the product will be like this. So you get a single bond now, and now this will be the CH2 and the CH3 there. The chlorine will be over here. This is the Markovnikov's product, right? This is the Markovnikov's product. What will be the anti-Markovnikov product? In an anti-Markovnikov product, the hydrogen will then attack over here, right? But that will be formed in a very small quantity, right? That will not be a major product. So hydrogen will go over here, and this particular carbon gets the chlorine and the CH3. This is the minor product, right? This is not the major product. And this will be called as an anti-Markovnikov product, right? This one will be a major product. Now let's see how the water molecule adds across a double bond. Addition of water again follows the Markovnikov's rule. Here again, the hydrogen is added to that double bond in carbon that has more number of hydrogen atoms. Okay, so that means hydrogen electrophile will attack on this particular carbon, and the hydroxide will go to the central carbon here, and you get the alcohol like this: CH3C, CH3, CH2 will now convert into CH3, and this particular carbon, the central carbon, it gets the OH. So you get the alcohol, and it again follows what? The Markovnikov's rule. Exactly the same, in the same manner in which HCl adds or any other asymmetrical reagent adds. So let's see here the mechanism of this particular reaction. In the first step here, alkene molecule reacts with the electrophile, and the reaction, actually we start with the proton, which acts as a catalyst, and this proton attacks on this carbon and forms a bond with this CH2. The pi electrons actually shift towards this carbon, and you get a carbocation, right? So you get CH3, and now the pi electrons form a bond with this proton, and it forms the CH3. The central carbon gets a positive charge, so you get a carbocation. And then in the second step, the same carbocation now will be under the attack of water, H2O molecule, right? So water with the low number of electrons can act as a nucleophile, and it can attack on the carbon, right? Forms a bond with this, and it forms an intermediate like carbon with the OH, H and H, positive charge on the carbon, and you get the CH3, CH3, and then one of the hydrogen atom is lost here as H plus, and you get the CH3, COH, CH3, and the CH3 here. Okay, so here is the loss of proton, the same proton that we use as a catalyst. So these are the two important steps in the addition of a water to the alkene. If for example the same proton attacks on this carbon, then in that case the carbocation will be a 1 degree carbocation, right? So in that case you get the OH on the terminal carbon, but that is relatively less stable, so that will be a minor product. So you also get another product while you have OH on the terminal carbon, right? So that will be the anti-Markovnikov's addition, but that is always a minor product, not a major product. Let's take another example. Here this is an alkene. The two carbon atoms, with this carbon, it has a one hydrogen atom. This one does not have any hydrogen atom. So when water adds across this double bond, so it again follows the Markovnikov's rule. Again, the hydrogen will go to this carbon, and the hydroxide will attack on this particular carbon. So you get a product like this: CH3, CH3, OH on this one, and this particular carbon gets one more hydrogen, so you get this product here. Again, the addition is as per the Markovnikov's rule. There will be a anti-Markovnikov addition also, but that compound will always be a minor product, and the minor product can be written like this, where the addition is anti-Markovnikov. Here in this case, the carbon with less number of hydrogen atoms gets a hydrogen, right? And therefore OH will be here, and you get a different product. But this is always a major product. This is the product that you get as per the Markovnikov's rule, and this one is always a minor product because that is a anti-Markovnikov addition, right? This is formed by the anti-Markovnikov addition. So let's take another example. This one again, this is an asymmetrical alkene. When addition occurs here, right? When addition of water occurs here, so it again follows the Markovnikov's rule. Hydrogen will go to this particular carbon and the OH will attack on this one, right? So OH will be here and the hydrogen will be here. So what do you get the product? You always get a product like this. The CH2 will now convert into CH3 and the OH will be over here, right? So let's see again the mechanism, right? In the first, the first step here, what do you get? By the attack of a proton, right? So when the proton attacks on it, so you get a carbocation like this. CH2 will change into CH3 and this particular carbon gets a positive charge, a carbocation, right? And then in the second step here, the hydroxide ion will attack on it and you get this product, right? So hydroxide ion will attack on this and you get this product. So this is the carbocation that you get as an intermediate. Hope you got the concept. Thanks for watching the video. Bye for now.